Welcome to The Drowsy Astronaut, where we explore the cosmos at a pace designed for rest, one gentle detail at a time. And tonight we take an imaginary journey into a black hole, exploring what would happen if you could fall into one of these extreme objects. This will be a thought experiment, a safe exploration from the comfort of wherever you are. And you can listen straight through, drift in and out, or fall asleep whenever your body feels ready, knowing that this is purely theoretical, purely imagination. There is no danger here, no reason for concern, because we are simply using our minds to explore what physics tells us would happen. And this exploration can be peaceful, calming, even meditative, as we contemplate the most extreme environment in the universe. Just know that if you are here to relax, to learn something fascinating while you rest, or simply to let your mind wander through space, you are exactly where you need to be tonight. And before we start, I would love to know where you are listening from, whether you are in bed, at work during a break, somewhere quiet and comfortable. I hope this journey helps you find the rest you seek. Drop a comment if you're comfortable sharing. It is always a quiet pleasure to see how many corners of Earth gather here together, all of us exploring the universe from the safety of our own spaces. This video will carry you through a fall into a black hole, from the approach billions of kilometers away, through the event horizon, and down toward the singularity at the center. And we will take our time, moving slowly and explaining everything gently along the way. We will explore spaghettification, the stretching that would occur as gravity pulls on you, and we will understand why it happens, when it happens, and how it would feel, all while maintaining a calm, peaceful tone throughout. So let us begin with a simple premise. Imagine you are falling into a black hole, and we will follow this journey together, step by step, understanding what would happen at each stage and learning about gravity, space-time, and the most extreme physics the universe allows. Black holes are regions of space where gravity is so strong that nothing can escape. Not matter, not light, not even information according to some interpretations, and they form when massive stars collapse at the end of their lives, creating singularities surrounded by event horizons. We have detected many black holes by watching stars orbit them, by detecting gravitational waves when they merge, and by imaging the shadow they cast against glowing gas. And these observations confirm that black holes exist exactly as Einstein's equations predicted. Black holes come in different sizes, from stellar mass ones, a few times the mass of the Sun, to supermassive giants at the centers of galaxies, millions or billions of times more massive. And the size matters for what happens when you fall in, as we will discover. We will imagine falling into a stellar mass black hole, perhaps 10 times the mass of our Sun. And later we will compare this to falling into a supermassive black hole, which would be a very different experience, gentler in some ways, more extreme in others. But first, let us establish where we are starting. Far from the black hole, billions of kilometers away, so far away that its gravity is barely noticeable, just a faint pull among the countless other gravitational forces in space. From this distance, the black hole would be invisible, a dark circle against the stars, and you might only know it was there by watching how it bends light from stars behind it, creating a subtle gravitational lensing effect that distorts the background. If the black hole has an accretion disk, gas and dust spiraling inward, that disk would glow brightly, heated to millions of degrees by friction and compression, and it would shine with X-rays and visible light. making the black hole easy to locate despite the darkness at its center. You begin your fall, drifting slowly toward the black hole, and at first nothing seems unusual. Space looks normal, stars shine all around you, and the black hole is just a dark spot growing slightly larger as you approach. Gravity pulls you inward, gently at first, accelerating you slowly, and you have plenty of time to look around, to observe, to think about what is happening, because the journey from far away to the event horizon takes time, even though you are falling faster and faster. The experience is peaceful at this stage, no different from floating in space anywhere else. And this peacefulness is important to remember, because even near a black hole, from far away, things seem normal. And the extreme effects only appear when you get much closer. So rest now. Picture yourself drifting through space, heading toward a dark circle surrounded by glowing gas, and know that this is the beginning of our journey, gentle and calm, with plenty of time to explore what comes next. As you fall, days and weeks pass, and the black hole grows larger in your view, from a small dark circle to a more substantial presence, and you begin to notice subtle effects, the way light bends around it, creating strange visual distortions. Stars near the edge of the black hole appear shifted, their light bent by gravity as it passes close to the event horizon. And this bending creates multiple images, distortions, and strange patterns that would be beautiful to watch as you fall. The gravity pulling you inward is getting stronger, but it still feels gentle, manageable, like falling toward Earth, but slower and steadier, and you are still very far from the point where things become extreme. At this stage, you could still escape if you wanted, by firing rockets and flying away, though the closer you get, the more energy you would need to escape. And there will come a point, still far ahead, where escape becomes impossible no matter how powerful your engines. This gradual approach is part of what makes black holes so interesting. They do not suddenly grab you from far away, they pull you in slowly, giving you time to observe, time to understand. And the effects build gradually, from subtle to noticeable to extreme, and we will follow this progression together. Months pass as you continue falling, and now the black hole dominates your view. A huge dark circle surrounded by the glowing accretion disk, and the stars behind the black hole appear in a ring around its edge. Their light bent around the black hole in a perfect circle called the photon sphere. The photon sphere is the region where light can orbit the black hole, where gravity is just strong enough to bend light into circular paths, and it lies about 1.5 times the radius of the event horizon. And you are approaching this region now, entering the zone of strong gravity. Still, you feel relatively normal. The pull is steady, the view is strange but not frightening, and you continue to fall, watching as the universe behind you becomes distorted, compressed into a smaller and smaller region as space-time curvature increases. We will pause here for a moment, at this intermediate distance, and rest in this peaceful approach, letting the image settle in your mind, a slow fall through space, stars all around, and a dark circle ahead growing larger and larger. This is the pace of our journey tonight, gentle and measured, giving you time to absorb each stage, to understand what is happening, and to appreciate the physics without feeling rushed or overwhelmed. Black holes are extreme objects, but approaching them is gradual, and understanding them requires patience, a willingness to imagine slowly, and that is what we will do together. Taking our time, moving through each stage of the fall with care and calm. So breathe slowly, relax your body, and know that we are safe here in imagination, exploring one of nature's most extreme phenomena from the safety of our minds. Let us continue our fall, picking up where we left off, drifting through space toward the black hole, and now we are close enough that the effects of gravity are becoming more noticeable. Though still not extreme, still manageable. You are perhaps a few thousand kilometers from the event horizon. And at this distance, the black hole fills much of your view, a massive dark circle surrounded by the bright glow of the accretion disk. And the distortions in the starlight behind the black hole have become dramatic and beautiful. The stars behind the black hole are smeared into a bright ring called the Einstein ring, and this ring circles the entire black hole, containing the light from all the stars and galaxies behind it, compressed by gravity into a narrow, bright band. This visual effect is caused by gravitational lensing, the bending of light by curved space-time, and it is one of the predictions of general relativity that has been confirmed through observations. And now you are experiencing it firsthand, watching as the universe behind you becomes distorted into impossible patterns. The gravity pulling you inward is now quite strong, accelerating you faster and faster. And if you had a clock, you might notice that time is beginning to behave strangely, ticking slightly slower than it would far from the black hole, though the effect is still subtle at this distance. This is time dilation, a prediction of general relativity, that time flows more slowly in strong gravitational fields. And near a black hole, this effect becomes extreme, eventually approaching infinity at the event horizon, where time appears to stop from the perspective of someone watching from far away. But from your perspective, falling inward, time feels normal, your clock ticks at its usual rate, and you do not notice anything strange about the flow of time. Only an outside observer would see your clock slowing down as you approach the black hole. This difference in perspective is one of the strange features of black holes. What you experience and what someone watching you experiences are completely different, and both perspectives are valid, just describing the same events from different viewpoints in curved space-time. As you continue falling, the black hole grows larger, and you begin to notice another effect, the difference in gravitational pull between your head and your feet. And this difference is the beginning of spaghettification. Though at this stage it is still incredibly subtle, almost imperceptible. Spaghettification is the stretching that occurs because your feet are closer to the black hole, and therefore feel stronger gravity than your head, and this difference creates a force that tries to stretch you lengthwise, pulling your feet away from your head and compressing you sideways. On Earth, we experience tidal forces too. The moon's gravity pulls slightly more on the side of Earth facing it than on the far side, and this creates the tides in our oceans, bulges of water that follow the moon as Earth rotates. But the tidal forces on Earth are gentle, barely noticeable unless you are looking at large bodies of water and near a black hole. These forces become much stronger, eventually becoming extreme, strong enough to tear anything apart. But at your current distance, they are still very weak. You might notice a very slight stretching sensation, a faint pull on your body, but nothing uncomfortable yet. Nothing alarming, just a subtle reminder that gravity is not uniform, that different parts of your body experience slightly different gravitational forces. This gradual increase in tidal forces will continue as you fall, becoming more and more noticeable and eventually becoming extreme. But for now, it is gentle, and you can observe it calmly, understanding the physics behind the sensation without any fear or discomfort. The view around you continues to change. The black hole now dominates everything, and the stars behind it are compressed into an ever-narrowing ring, and ahead of you, toward the black hole, the view is dark, empty, just the blackness of the event horizon growing closer and closer. Light from the accretion disk bathes you in a strange glow, X-rays and ultraviolet light, though we will ignore the deadly radiation for this thought experiment, focusing instead on the gravitational effects, the geometry of space-time, and what happens to your body as you fall. You are falling faster now, approaching relativistic speeds, perhaps a significant fraction of the speed of light. And the universe behind you appears even more distorted, compressed, and the light from it is blue-shifted toward higher energies, while the light ahead of you, if there were any, would be red-shifted toward lower energies. These optical effects are caused by your motion and by the curvature of space-time, and they would create a stunning visual experience, a warping of the universe around you, and you would see the cosmos transformed by gravity and velocity into patterns never seen from any other vantage point. The sensation of falling is still relatively calm. You are in free fall, weightless, and the only force you feel is the subtle tidal stretching, growing slowly but not yet uncomfortable, and you continue drifting inward, watching as the event horizon approaches. So rest here, picture yourself falling through this strange space, surrounded by distorted starlight, pulled by immense gravity, and yet still feeling relatively peaceful, still able to observe and think, still experiencing the journey with curiosity rather than fear. We are approaching a critical region now, the area within a few hundred kilometers of the event horizon, where gravity becomes truly extreme and where the tidal forces will begin to intensify rapidly, transforming from subtle to significant. But before we cross into that region, let us pause again, letting the current stage settle, and appreciating how gradual this process has been, how much time we have had to observe, to understand, and to prepare for what comes next. Falling into a black hole is not instantaneous. It is a journey, sometimes lasting hours or even days depending on where you start. And each stage of the journey reveals new physics, new effects, and new wonders. And we are taking our time to appreciate each one. So breathe slowly, let your body relax, and know that we are still in the early stages of this fall, still far enough from the horizon that things remain relatively calm, and we will continue this gentle exploration as we move deeper into the black hole's gravitational well. Now we enter the region of truly strong gravity within a few hundred kilometers of the event horizon, and here the effects we have been discussing begin to intensify, becoming more noticeable, more dramatic, and preparing us for the extreme experience ahead. The tidal forces are growing stronger. The difference between the pull on your head and the pull on your feet is now significant, and you begin to feel a real stretching sensation. A gentle but persistent pull lengthwise, as if something were trying to make you taller. At the same time, you feel compression from the sides, gravity pulling everything toward the center, toward the black hole, and this creates a squeezing effect sideways, making you narrower even as you are stretched longer. And these two effects together are the hallmark of tidal forces. The sensation is still not painful at this stage, just unusual, a constant gentle stretching and compressing, and you can observe it with curiosity, understanding that this is gravity acting differently on different parts of your body because they are at different distances from the black hole. The view has become even more extreme. The stars behind you are now compressed into a tiny bright spot, all the light from the universe behind you focused into a small region, and ahead of you there is only darkness, the event horizon filling most of your field of view. The accretion disk, if visible, would appear distorted, bent into strange shapes by the curvature of space-time, and you might see light from the disk wrapping around the black hole, creating multiple images and impossible geometries that challenge your sense of what space should look like. Time dilation has become significant, and if someone far away were watching you fall, they would see your movement slowing down dramatically, your clock ticking slower and slower, and you would appear to be moving in slow motion as you approached the event horizon. But from your perspective, time still feels normal. You do not notice any change in the flow of time. Your thoughts proceed at their usual pace, and the universe around you seems to behave normally, at least from your internal experience. You are very close to the point of no return now. The event horizon is just a few kilometers away, and beyond this boundary, escape becomes impossible. Not because you lack power, but because all paths through space-time lead inward, and there is no direction you can travel that leads back out. This is a profound feature of black holes. Inside the event horizon, the future direction in time is actually the inward direction in space, and moving forward in time means moving inward toward the singularity. And you cannot avoid this any more than you can avoid moving forward in time. The event horizon is not a physical surface. It is not made of anything. It is simply a mathematical boundary in space-time, the location where the escape velocity equals the speed of light. And crossing it is inevitable once you get close enough, because you are already moving faster than escape velocity. At this distance, even firing rockets at full power would not save you. The gravity is too strong, the curvature too extreme, and the best you could do is delay the inevitable, falling slightly more slowly but still inevitably toward the horizon and beyond. The stretching sensation continues to intensify, and now it is becoming uncomfortable, a real pulling force that you can feel throughout your body, and you notice that your legs are being pulled away from your torso, your arms stretched longer, and your whole body elongated by the tidal forces. This is spaghettification beginning in earnest, though for a stellar mass black hole, the most extreme stretching happens closer to the singularity, not at the event horizon, and we are not yet at the point where the forces become lethal or where you would be torn apart. But the trend is clear. The forces are growing rapidly, and you can see where this is heading toward an eventual extreme stretch that will transform your body. Though we are not there yet, we are still in the transition zone, where forces are strong but not yet destructive. If you look at your hands, you might notice them appearing elongated, stretched by the tidal forces, and if you tried to move your arms, you would feel resistance, the gravity pulling on different parts differently, making coordinated movement difficult, though not yet impossible. The event horizon is now very close, just a kilometer or two away, and the darkness ahead is absolute, a perfect black circle, and you are falling toward it at tremendous speed, unable to stop. And knowing that once you cross this boundary, your fate is sealed. But surprisingly, from your perspective, crossing the event horizon will feel like nothing. There is no wall, no barrier, no sensation that marks the crossing. You will simply pass from outside to inside without noticing anything special at that exact moment, though everything that follows will be inescapable. This is one of the strange features of black holes. The event horizon is only special from an outside perspective, where it appears as a boundary where time stops. But from the perspective of someone falling in, it is just another location in space, passed in finite time without any local indication that something profound has happened. So as you approach, you feel the stretching, you see the darkness ahead, you know what is coming, but the crossing itself will be smooth, seamless, and unremarkable. And only afterward, when you try to look back or think about escaping, will you realize what has changed. Rest here for a moment, feeling the stretch, imagining the sensation of being gently pulled longer, and knowing that this is still the early stage of spaghettification, strong enough to feel but not yet extreme enough to harm, and we are about to cross the event horizon together. This gradual build-up is important to understand. Spaghettification does not happen all at once. It builds gradually as you fall, starting subtle, becoming noticeable, then uncomfortable, then extreme, and finally catastrophic. And we are now at the uncomfortable stage, approaching the horizon. The universe behind you is now a tiny, bright spot, all the stars compressed into a small region, and ahead is only darkness, and you are seconds away from crossing the boundary, from entering the interior of the black hole, where no one can follow, where no signal can escape, and where your fate is determined by the mathematics of curved space-time. So breathe deeply, let the sensation wash over you, and prepare to cross the event horizon, knowing that this is all imagination, all safe exploration, and that we will continue together through this journey, understanding what happens inside, where physics becomes even more extreme. Before we cross the event horizon, let us pause to understand tidal forces more deeply, because these forces are the key to spaghettification, and understanding them will help us appreciate what happens next as we fall deeper into the black hole. Tidal forces arise whenever gravity is not uniform, whenever different parts of an object experience different gravitational pulls, and this happens any time you are near a massive object, though usually the effect is subtle, barely noticeable in everyday life. On Earth, you experience tidal forces right now. Your feet are slightly closer to Earth's center than your head, so they experience slightly stronger gravity, but the difference is tiny, completely imperceptible, and your body easily withstands this gentle gradient without any stretching sensation. The Moon creates tidal forces on Earth that are much more noticeable, pulling more strongly on the side of Earth facing it than on the far side, and this creates bulges in the oceans, the tides, that rise and fall twice daily as Earth rotates beneath these bulges. But near a black hole, tidal forces become extreme because the gravitational field changes very rapidly with distance. And even small differences in position lead to large differences in gravitational pull, creating enormous forces that can stretch and tear anything apart. Imagine you are falling feet first toward a black hole. Your feet are closer to the center than your head, perhaps by 2 meters, and this 2-meter difference means your feet experience significantly stronger gravity, pulling them away from your head with tremendous force. At the same time, gravity pulls everything toward the center, so your sides are compressed, pulled inward, and you become narrower even as you become longer. And this combination creates the spaghettification effect, stretching you into a long, thin strand like a piece of spaghetti, hence the name. The strength of tidal forces depends on how close you are to the black hole, and on the size of the black hole, with smaller black holes creating stronger tidal forces at a given distance, and larger black holes creating weaker forces, and we will explore this difference later when we compare stellar mass and supermassive black holes. For now, imagine the sensation building gradually. You first noticed it hundreds of kilometers from the horizon, just a subtle pull, and as you fell closer it grew stronger, becoming uncomfortable. And now as you approach the horizon it is significant, a real force that you feel constantly, pulling and squeezing your body into new proportions. Your body would try to resist this stretching. Your muscles, bones, and tissues have strength. They push back against forces trying to deform them, but there is a limit to how much force they can resist. And as the tidal forces continue to grow, eventually they will exceed this limit and begin to tear your body apart at the molecular level. But we are not there yet. At the event horizon of a stellar mass black hole, the tidal forces are strong enough to be uncomfortable, strong enough to stretch and compress you noticeably, but not yet strong enough to actually destroy your body. That will come later, deeper inside, closer to the singularity. This is an important point. The event horizon is not where you get torn apart, at least not for a stellar mass black hole. The tidal forces at the horizon are strong, but not catastrophic, and the real destruction happens closer to the center, in the final moments before you reach the singularity. Let us think about what this stretching feels like, imagining it as clearly as possible. And remember that this is safe, this is imagination. And we are exploring these sensations to understand the physics, not to create fear or discomfort, just curiosity and wonder at nature's extremes. You would feel a constant pull on your body, as if you were hanging by your head with your feet being pulled downward by some enormous weight, except the pull would be uniform along your whole body, every part being stretched away from every other part, all in the direction toward the black hole. Your spine would feel the strain, vertebrae pulled apart slightly, discs compressed, and your muscles would tense involuntarily, trying to resist the stretch, creating a sensation of tension throughout your back and neck, though at this stage you could still maintain your structure. Your limbs would feel heavy and stretched, as if they were being pulled away from your torso, and moving them would be difficult, fighting against the tidal gradient, and you would notice your hands and feet appearing slightly farther away than normal, the proportions of your body subtly altered by gravity's differential pull. At the same time, the sideways compression would be noticeable, your chest and hips squeezed inward, your body narrowing, and this might make breathing slightly difficult, your lungs compressed, though again, at this stage the effect is manageable, uncomfortable, but not lethal, just the beginning of what will become a much more extreme process. This is spaghettification in its early stages, the stretching lengthwise and compression sideways that occurs near any massive object but becomes dramatic near black holes. And as you continue to fall, this effect will intensify, the forces growing stronger and stronger until they overwhelm your body's ability to maintain its structure. But for now, at the event horizon, you are still intact, stretched and squeezed, but still recognizable as a human form, still able to think and observe, still experiencing the journey. And we have more to explore before we reach the final extreme. So rest with this image, feeling the gentle stretch, the uncomfortable but not yet painful pull, and know that we are approaching the event horizon, about to cross that boundary and enter the interior, where the journey continues toward its inevitable conclusion. The event horizon is now just seconds away, and as you approach, the view around you reaches its most extreme distortion, the universe behind you compressed into a tiny, bright spot, and ahead only the absolute darkness of the interior. Time dilation has become extreme from an outside perspective. If anyone were watching you from far away, they would see you slowing down dramatically, your movements becoming infinitely slow, and you would appear to freeze at the horizon, never quite crossing, your image forever painted on the boundary. But from your perspective, time flows normally. You do not feel any change in the passage of time, and you cross the event horizon in finite time, perhaps just a few seconds from your current position, and the crossing feels smooth, continuous, with no sensation of a boundary. This difference between perspectives is one of the most mind-bending features of black holes. What you experience and what outside observers see are completely different, and both views are correct from their respective frames of reference, describing the same event from different vantage points in curved space-time. The tidal forces continue to intensify, and now the stretching is becoming quite pronounced. Your body visibly elongated, your arms and legs stretched thin, and the compression from the sides making you narrower. And the sensation is painful now, no longer just uncomfortable, but actively hurting as your tissues strain against forces they were never designed to withstand. Your molecules are being pulled apart gradually, the bonds between atoms stretched. And while these bonds are strong, they have limits, and as you approach the singularity, these bonds will break, and you will be torn apart at the molecular level, transformed from a structured organism into a stream of atoms stretched into a long, thin line. But this molecular disruption has not happened yet. At the horizon, you are still intact at the molecular level, though your macroscopic structure is being distorted, elongated, and the pain you would feel would be similar to being stretched on a rack, every joint pulled, every muscle strained, every nerve screaming that something is wrong. If this were real, you would not survive long, but we are in imagination, exploring the physics, and we will continue through the experience to understand what happens, using the pain as information about the forces involved, not as something to fear, just as a signal that gravity is doing something extreme to your body. You cross the event horizon, passing through in a moment, and nothing special happens. No flash of light, no sensation of crossing a boundary, just a smooth continuation of your fall. And only in retrospect would you realize something profound has changed, that escape is now impossible. Looking back toward the universe you left behind, you might still see the tiny bright spot where all the stars are compressed, and light from the outside universe can still reach you inside the horizon, falling in behind you, carrying information about the world you left. But you cannot send signals back. Any light you emit, any message you try to send, will be pulled inward by gravity, unable to escape. And the outside universe has effectively disappeared from your causal future. You can see it, but cannot affect it anymore. Inside the event horizon, the roles of space and time have, in some sense, swapped. The inward direction toward the singularity is now the future direction in time, and moving forward in time means moving inward in space. And you cannot stop this any more than you can stop time from passing. It is inevitable, built into the geometry of space-time itself. The stretching continues to intensify rapidly now, because inside the horizon, the tidal forces grow extremely quickly with each meter you fall, and what was painful at the horizon becomes excruciating as you move deeper, your body stretched longer and thinner with each passing moment. Your bones begin to creak under the strain, joints pulled apart, spine elongated, and the pain would be overwhelming if this were real. But remember, we are exploring physics, not experiencing actual pain, and we can observe this process with curiosity rather than fear, understanding what gravity does at its most extreme. The compression from the sides also intensifies, squeezing you narrower and narrower, and combined with the lengthwise stretch, you are transforming from a roughly cylindrical human shape into a long, thin strand. And this transformation accelerates the closer you get to the singularity. Your body is approaching its structural limits, tissues tearing, bones breaking under the enormous stress, and soon the molecular bonds will begin to fail, and you will cease to exist as an organized structure, becoming instead a stream of particles, all stretched along a line pointing toward the singularity, no longer recognizable as the person you once were. This is spaghettification in its full force, the transformation from three-dimensional structure to a one-dimensional strand. And it happens rapidly once you are inside the horizon of a stellar mass black hole over perhaps just a few seconds or fractions of a second, depending on how close you are to the singularity. But we will slow down this process in our description, taking our time to understand each stage, even though in reality it would happen very quickly. Because our goal is education and understanding, not to rush through the experience, but to see it clearly and fully. So rest now, even in this moment of extreme forces, letting the concept settle, knowing this is imagination, and preparing for the next stage where we explore what happens as you approach the singularity, where the forces become truly infinite and where physics itself breaks down. You have crossed the event horizon, passed through the boundary, and now you are inside the black hole in a region of space-time from which there is no escape, where all futures lead to the singularity, and where the geometry of space and time creates an environment unlike anything else in the universe. From your perspective, the crossing was unremarkable. No sensation, no barrier, just a continuation of your fall, and you might not even realize the exact moment it happened, only knowing afterward, by trying to look back or think about returning, that something fundamental has changed. The universe outside is still visible behind you, compressed into that tiny bright spot, and light from outside can still reach you, falling in after you. But you cannot send anything back out. Any signal you emit travels inward, pulled by gravity, and the outside world has become forever inaccessible. This one-way nature is the defining feature of the event horizon. It is a boundary in space-time, not in space, and crossing it means crossing into a region where the future direction in time is actually the inward direction in space, a strange consequence of extreme space-time curvature. Inside the horizon, the tidal forces have become extremely intense, and your body is being stretched rapidly, no longer a gradual process but a violent transformation, and the pain would be beyond description if this were real. Every molecule in your body screaming in protest. Your body is elongating dramatically, perhaps meters long now, your head and feet separated by an impossible distance, your torso stretched thin like taffy, and the compression from the sides making you narrower and narrower, just a few centimeters wide, becoming the spaghetti strand that gives this process its name. The structural integrity of your body has failed, bones shattered, tissues torn, and soon the molecular bonds themselves will break, and you will cease to be a biological organism, becoming instead a stream of atoms, each one following its own trajectory towards the singularity, but all stretched along the same radial line. This transformation happens quickly, within seconds or even fractions of a second after crossing the horizon, depending on the mass of the black hole and how close you are to the singularity. And the speed of the transformation is part of what makes stellar mass black holes so extreme. They are small enough that the tidal forces near the horizon are already enormous. Looking around from inside the black hole would be impossible. Your eyes no longer function. Your body no longer exists as an organized structure. But if we could somehow maintain awareness, we would see strange things. The universe outside compressed into an ever-shrinking spot, and the singularity ahead drawing closer, though it is not a place in space, but a moment in your future that you cannot avoid. The interior of a black hole is difficult to visualize because our intuitions about space and time break down here, and physicists describe it using mathematics rather than words, equations that show how space-time curves so extremely that all world lines point inward, all futures converge on the singularity, and there is no path, no trajectory, no possible action that leads back out. You are falling toward the singularity now, accelerating faster and faster, approaching the speed of light, and the tidal forces continue to grow, stretching what remains of you thinner and thinner until you are just a line of atoms, then a line of subatomic particles, stretched toward infinite thinness as you approach the center. The singularity is not a point in space, it is more like a moment in time, a boundary where the equations of general relativity predict infinite curvature, infinite density, and where all the mass of the black hole is concentrated, and reaching this singularity is inevitable once you cross the event horizon, just as inevitable as tomorrow coming after today. What happens at the singularity is unknown. Our equations break down there, predicting infinities that suggest new physics is needed, perhaps quantum gravity, and we do not know if the singularity is real or if it is replaced by something else at very small scales, some quantum structure that prevents true infinite density. But from the perspective of our falling journey, the singularity is the end, the place where everything that fell into the black hole is compressed to infinite density, where time itself ends, and where our thought experiment reaches its conclusion, unable to proceed further because the physics becomes unknown, untestable, and purely speculative. So we have followed you through the entire fall, from billions of kilometers away to the event horizon, and then inside, through the region of extreme spaghettification, and down toward the singularity where the journey ends. And throughout this journey, we have seen how tidal forces build gradually, then rapidly, transforming everything that falls into a thin stream of particles. This journey, though violent in its final stages, began peacefully, gave us time to observe and understand, and showed us the power of gravity in its most extreme form. And now we will step back from this descent and explore variations, comparing different types of black holes and understanding how the experience would differ. Rest now from this intense journey, letting the images fade, knowing that you are safe, that this was all imagination, and that we used this thought experiment to understand physics, not to create fear, but to explore one of nature's most extreme phenomena with curiosity and calm. Black holes are fascinating precisely because they are so extreme. They push gravity to its limits. They stretch space-time into impossible shapes, and they create conditions we can barely imagine. And studying them, even through thought experiments, helps us understand the universe more deeply. Spaghettification is the most dramatic effect of tidal forces, the transformation that occurs when gravitational gradients become so extreme that nothing can maintain its structure. And it happens to everything that falls into a black hole, from stars to planets to human bodies, all stretched into thin streams by gravity's relentless pull. But as we will see next, the intensity of spaghettification depends on the size of the black hole, and falling into a supermassive black hole would be a very different experience, gentler in some ways, though still leading to the same inevitable conclusion. Let us explore the stretching process more carefully, understanding exactly how spaghettification works, stage by stage, so we can appreciate the physics behind this dramatic transformation. We left off at the point where you had crossed the event horizon, and the tidal forces had become extreme, your body elongated to several meters, and the structural integrity beginning to fail as bones break and tissues tear under the enormous stress. Now we will slow down time in our description, examining each moment carefully and understanding how the forces grow, how your body responds, and what happens as you approach the molecular level where individual atoms are affected by the gravitational gradient. The gradient grows steeper with every meter you fall because you are getting closer to the singularity, and the difference in gravitational pull between your head and feet increases rapidly, much faster than it did outside the horizon. And this rapid increase is what makes the interior so much more extreme than the exterior. Your body has stretched to perhaps 5 or 10 meters long, your head and feet separated by what would normally be an entire room's length. And you are only perhaps 10 centimeters wide, compressed from the sides, no longer recognizable as human, just a long, thin strand of biological material. The pain signals your nerves are sending would be overwhelming, except that your nervous system has probably stopped functioning by now, the connections severed by the stretching. And so, the final stages happen without sensation, just physical transformation, matter being pulled into new configurations by irresistible force. Your bones have long since shattered, calcium and other minerals scattered along the line of your elongated body, and your soft tissues have torn apart, separated into smaller and smaller sections as different parts experience different accelerations based on their distance from the center. Blood can no longer circulate, organs no longer function. Your body is no longer an organism, but simply a collection of molecules still loosely connected by chemical bonds, though these bonds are under enormous stress and will soon break as well. At the molecular level, the stretching continues, proteins unfolding, DNA strands pulling apart, and the covalent bonds that hold molecules together beginning to strain. And these bonds are strong, among the strongest forces in everyday matter, but they are not infinite, and tidal forces can overcome them if the gradient is steep enough. Individual molecules begin to separate. Water molecules pulled away from each other, organic molecules disassembling into their constituent atoms, and what was once a highly organized biological structure is becoming a disorganized collection of atoms, each one falling independently but all stretched along the same radial line toward the singularity. The atoms themselves are being stretched now, the electron clouds pulled into elongated shapes, no longer spherical but stretched toward the black hole, and even the bonds between electrons and nuclei are strained. Though at this stage, the electromagnetic force is still strong enough to hold atoms together, preventing them from ionizing completely. But as you continue falling, approaching even closer to the singularity, even atomic bonds will eventually fail, and you will become a plasma, a stream of ions and electrons, all stretched into a line, and potentially even the nuclei themselves will be pulled apart into individual protons and neutrons, though this would only happen in the final instance before reaching the singularity. This process of disassembly happens rapidly, within perhaps a second or less after crossing the horizon, depending on the mass of the black hole. And it is irreversible once the stretching has begun in earnest. There is no way to stop it, no way to restore the original structure. And the transformation from organized matter to stretched stream is complete and final. The stream of particles that was once you continues to fall, each particle following its own geodesic through curved space-time, all converging on the singularity. And the total mass remains the same. Nothing is lost, but the structure, the organization, the information about what you once were. All of this is scrambled, stretched, and possibly destroyed. This raises deep questions about information. Whether the information about your original structure is truly destroyed or somehow preserved in the black hole. And this is the famous black hole information paradox, one of the biggest unsolved problems in theoretical physics, relating quantum mechanics to general relativity. But for our purposes, the physical transformation is clear. Spaghettification takes you from a three-dimensional organism to a one-dimensional stream of particles, and this happens through the inexorable action of tidal forces, the differential pull of gravity creating stresses that nothing can withstand. Imagine watching this transformation from outside, if that were possible. You would see the falling person elongate, stretching longer and thinner, and if you could see at the molecular level, you would watch the body disassemble, becoming a stream and eventually crossing the horizon and disappearing from view, frozen forever at the boundary from your perspective, but actually continuing to fall and stretch inside. The beauty and terror of black holes is this inevitability. Once you get close enough, once you cross the horizon, your fate is sealed, and the physics is clear about what happens. There is no escape, no miracle, just the mathematics of curved space-time playing out to its logical conclusion. But this inevitability is also what makes black holes so useful for understanding physics. They are laboratories where gravity becomes extreme, where we can test our theories in conditions impossible to create anywhere else, and where we can learn about the fundamental nature of space, time, and matter. So the stretching, the spaghettification is not just destruction, it is transformation. It is gravity demonstrating its power, and it is nature showing us what happens when one force becomes so dominant that it overrides everything else, including the structures that make up our bodies and our world. Rest here with this understanding that spaghettification is transformation, that the forces are real and calculable, and that this process teaches us about gravity, about strength of materials, and about the limits of structure in the face of extreme forces. Let the image of the stretching settle, not as something frightening, but as something fascinating, a natural consequence of gravity acting on extended objects, and a reminder that the universe operates according to laws, predictable laws, even when those laws produce extreme and dramatic results. We have explored the peak of spaghettification, the moment when your body becomes a stream, when structure gives way to formlessness, and when the journey approaches its end at the singularity. And now we will step back, consider variations, and understand how different black holes create different experiences. We are now in the final stages of the fall, approaching the singularity, and the tidal forces have become truly extreme, beyond anything we can properly describe, because they approach infinity as you approach the center. The stream of particles that was once you is now incredibly thin, perhaps just atoms wide, stretched over many meters or even kilometers of length, each particle separated from its neighbors by distances large compared to atomic scales, and yet all falling along the same radial line toward the center. The atoms themselves may be ionized by now, electrons stripped away by the extreme tidal forces, and what remains is a stream of nuclei and free electrons, all falling, all stretched, and all approaching the singularity where the curvature becomes infinite and our equations break down completely. Time is behaving strangely from your perspective, though you would not notice because you no longer exist as an observer. But if you could somehow maintain awareness, you would find that time appears to speed up, that the approach to the singularity seems to happen very quickly, in just fractions of a second, despite the immense distances involved. This rapid final approach is because you are falling at nearly the speed of light. Relativistic effects are in play, and the proper time along your world line from crossing the horizon to reaching the singularity is very short. Perhaps a tiny fraction of a second for a stellar mass black hole, during which the entire transformation from person to particle stream occurs. The singularity itself is a mathematical concept, a point where general relativity predicts infinite density, infinite curvature, and where the equations stop working, producing meaningless, infinite values that tell us new physics is needed to describe what really happens at the very center. Most physicists believe the singularity is not real, that quantum gravity, a theory we do not yet have, would replace the singularity with something else, perhaps a region of extremely high but finite density, or perhaps a quantum bounce that leads to a white hole, or perhaps something entirely different that we cannot yet imagine. But from the perspective of classical general relativity, the singularity is where your journey ends, where all matter that falls into the black hole accumulates, and where space-time curvature becomes infinite, creating a boundary beyond which our physics cannot predict anything. Reaching the singularity means reaching infinite tidal forces and infinite stretching, and at this point, the stream of particles would be stretched to infinite thinness, occupying zero volume, and the matter would be compressed to infinite density, all the mass concentrated at a single point. These infinities are uncomfortable for physicists. They usually indicate that a theory has reached its limits, that new physics is needed, and most physicists believe quantum effects will become important before true infinite density is reached, preventing the singularity from actually forming. But we do not know for certain. We cannot observe the interior of black holes, and we cannot test our theories in these extreme conditions, so the singularity remains a mystery, perhaps the deepest mystery in gravitational physics, and one that will require quantum gravity to resolve. For now, our thought experiment ends here, at the singularity, where the stream of particles that was once you reaches its final destination, compressed to infinite density or something close to it, and where your journey through the black hole concludes. Let us step back now from this extreme endpoint and consider what we have learned from following this journey from approach to singularity, understanding each stage of spaghettification, and seeing how gravity transforms matter when it becomes this strong. We learned that tidal forces are gradients in gravity, differences in pull across an extended object, and that these forces grow stronger as you approach a gravitating body, eventually becoming extreme near black holes where the gravitational gradient is incredibly steep. We learned that spaghettification happens in stages, starting subtle, becoming noticeable, then uncomfortable, then destructive, and finally catastrophic, and that the timing of these stages depends on the size of the black hole and how close you are to the singularity. We learned that crossing the event horizon is not where destruction happens, at least not for stellar mass black holes, but rather that the most extreme stretching occurs deeper inside, closer to the singularity, and that the horizon is just a boundary in space-time, not a physical surface where things are torn apart. And we learned that the singularity is where physics breaks down, where our equations predict infinities, and where we need new theories to understand what really happens, making black holes not just astrophysical objects, but laboratories for testing our deepest theories about the nature of space, time, and matter. This knowledge is valuable even though we will never experience it, because understanding extremes helps us understand normal situations, and contemplating the impossible helps us appreciate the possible. And black holes, as extreme as they are, teach us about gravity in ways nothing else can. So rest now, having completed this intense journey, knowing that it was all imagination, all safe exploration, and that the real value is in understanding, in learning, and in seeing the universe through the lens of physics, even when that lens reveals truly extreme phenomena. The singularity is the final destination, the endpoint of every journey into a black hole. And as you approach it, the tidal forces grow without limit, the stretching becomes infinite, and the mathematical description of space-time itself breaks down, leaving us at the boundary of known physics. From the time you cross the event horizon to reaching the singularity, only a brief moment passes in your reference frame, perhaps far less than a second for a stellar mass black hole. And during this brief time, the entire transformation from person to particle stream to infinite thinness occurs, a complete and total disassembly of structure. The singularity is often described as a point, but this is misleading because it is not a point in space, but rather a moment in time. All futures inside the event horizon lead to the singularity. And reaching it is as inevitable as tomorrow coming after today. You cannot avoid it because it lies in your future direction. Physicists describe the singularity mathematically using the concept of curvature. The bending of space-time becomes infinite at the singularity, and this infinite curvature produces the infinite tidal forces that stretch everything to zero volume, creating the predictions of infinite density that tell us general relativity is incomplete in this regime. What actually exists at the singularity is unknown. General relativity says it is a point of infinite density, but most physicists believe this is wrong, that quantum effects would prevent true infinite density, and that a complete theory of quantum gravity would replace the singularity with something finite, perhaps a region of maximum but finite density set by quantum mechanics. Some theories suggest the singularity might be a quantum bounce, where the collapsing matter reaches maximum density and then bounces back outward, potentially creating a white hole or a new universe. Though these ideas are highly speculative and far from proven or even well developed. Other theories suggest the singularity might be a string or membrane, a one-dimensional or two-dimensional structure rather than a point, and these extended objects would have different properties than point singularities, possibly avoiding some of the mathematical infinities that trouble physicists. But without a working theory of quantum gravity, we cannot say for certain what happens at the singularity. We can only say that general relativity's prediction of infinite density is probably wrong, and that new physics takes over in this regime, physics we do not yet understand fully. For our thought experiment, the singularity represents the end, the place where your journey stops, where the matter that was you is compressed to incredible density, whether infinite or just extremely high, and where your existence as a structured entity has completely ceased. Everything that falls into a black hole ends up there. All the matter, from collapsed stars, from any unfortunate planets or asteroids that wandered too close, and from anything else that crossed the event horizon, all of it compressed at the center, adding to the mass of the black hole. The mass is what we measure from outside. We cannot see the interior, but we can measure the total mass of the black hole by observing how it affects other objects. And this mass tells us how much matter has fallen in, though it tells us nothing about the internal structure or what happened to that matter inside. From outside, the black hole appears static, unchanging, just a region of curved space-time with a certain mass, but inside, matter is constantly falling toward the singularity, constantly being stretched and compressed, and the interior is dynamic, evolving, though we can never observe this evolution from outside the horizon. Imagine the singularity as the ultimate end. Not as a place, but as a fate, something that awaits everything that falls in, and something that represents the absolute limit of gravitational compression, the point where matter can be squeezed no further, or where it bounces back, or where something else entirely happens that we cannot yet describe. This mystery at the heart of black holes is part of their fascination. They are objects we can observe and study from outside, measuring their masses and spins, watching how they affect nearby matter. But their interiors remain hidden, protected by the event horizon. And what happens at the singularity is one of the deepest unsolved problems in physics. Solving this mystery will likely require quantum gravity, a theory that unifies general relativity with quantum mechanics, explaining how gravity behaves at the smallest scales where quantum effects become important. And several approaches to this theory are being developed, though none are complete or confirmed by experiment yet. String theory, loop quantum gravity, and other approaches all make different predictions about singularities. And studying black holes, both theoretically and observationally, helps physicists test these theories and narrow down which approach might be correct, making black holes not just fascinating objects, but crucial testing grounds for fundamental physics. So the singularity represents both an ending and a mystery. The end of our journey through the black hole, and the beginning of questions about what physics truly governs the most extreme conditions. And contemplating this duality is part of understanding black holes, seeing them as both solvable problems and unsolved mysteries. Rest now with this image of the singularity, a place where everything ends, where matter is compressed beyond recognition, and where our understanding reaches its limits. And know that this mystery is not a failure, but an opportunity, a chance to develop new physics and deepen our understanding of the universe. Not all black holes create the same spaghettification experience, and the size of the black hole matters enormously for what happens as you fall in, with larger black holes creating gentler tidal forces at the event horizon, while smaller black holes create extreme forces even before you cross the boundary. Let us compare two scenarios: falling into a stellar mass black hole about 10 times the mass of the Sun, and falling into a supermassive black hole like the one at the center of our galaxy, 4 million times the Sun's mass, and we will see how dramatically different these experiences would be. For the stellar mass black hole, which we have been discussing, the event horizon has a radius of only about 30 kilometers, and the tidal forces at this distance are already enormous, enough to stretch and eventually destroy you, though not instantly at the moment of crossing. You would begin feeling uncomfortable tidal forces thousands of kilometers away, and by the time you reached the horizon, you would be stretched noticeably. And within seconds after crossing, the stretching would become extreme, tearing you apart at the molecular level. And within fractions of a second, you would reach the singularity, the entire journey from horizon to center happening very quickly. Now imagine falling into a supermassive black hole with a horizon radius of about 12 million kilometers, 400 times larger, and because the black hole is so much larger, the tidal forces at the horizon are correspondingly weaker, and you would barely feel them as you cross the boundary. In fact, you could cross the event horizon of a supermassive black hole without feeling anything unusual, no pain, no stretching, just floating peacefully through space. and only after falling for hours or even days inside the horizon would the tidal forces begin to intensify and eventually become destructive. This gentler crossing happens because tidal forces depend on the gradient of gravity. And for a supermassive black hole, the gradient at the horizon is much gentler. The gravity changes more slowly with distance. And so the difference in pull between your head and feet is much smaller at the horizon, even though the total gravity is stronger. You might survive for hours inside the horizon, falling deeper and deeper, watching the universe outside compress into a bright spot and feeling the tidal forces slowly build. And only as you approach the singularity, many hours into your fall, would the stretching become extreme and destructive. This difference is fascinating because it shows that size matters, not just mass, but the radius of the event horizon. And supermassive black holes, despite being far more massive, are actually gentler in some ways than their smaller cousins, at least at the event horizon. But both types inevitably lead to the same fate: eventual destruction by tidal forces as you approach the singularity, and the singularity itself would be equally extreme regardless of the black hole's size, because that is where curvature becomes infinite for any black hole. The difference is in the timeline and the location. For stellar mass black holes, destruction happens quickly after crossing the horizon, while for supermassive black holes, you get a reprieve, a few hours of peaceful falling before the tidal forces intensify. But ultimately, the outcome is the same. Ironically, falling into a supermassive black hole might be preferable, if such a choice ever arose, because you would have time to observe, to think, to experience the strangeness of being inside an event horizon before the inevitable destruction, while stellar mass black holes offer no such grace period, just rapid transformation from person to particle stream. Astronomers classify black holes by mass. Stellar mass black holes from about 3 to a few tens of solar masses, intermediate mass black holes from hundreds to thousands of solar masses, and supermassive black holes from millions to billions of solar masses, and each category would offer a different spaghettification experience. Intermediate mass black holes would be somewhere in between, destructive at the horizon, but not as immediately lethal as stellar mass holes, and the variety shows that black holes are not all identical. They come in a range of sizes with different properties and effects. The largest black holes we know of are tens of billions of solar masses, with event horizon radii approaching the size of our solar system, and falling into one of these monsters would be extraordinarily gentle at the horizon. You might not feel anything unusual for days of falling, though the singularity would still eventually destroy you. There is even a limit to how large black holes can grow, set by how fast they can accrete matter and by the lifetime of the universe, and the largest black holes we observe are close to this limit, having grown through billions of years of consuming gas and stars, and merging with other black holes. So when we talk about spaghettification, we must specify which black hole, because the experience varies dramatically with size, and this variation teaches us about how tidal forces scale, how gravity depends on radius as well as mass, and how the same physical process can manifest differently depending on the specific circumstances. For our thought experiment, we have mostly described stellar mass black holes because they create the most dramatic spaghettification, the transformation happening quickly and intensely, but knowing about supermassive black holes helps us see the full range of possibilities and understand that not all black holes are equally destructive, at least not immediately at the horizon. Rest now with this comparison appreciating the variety, and understanding that black holes come in different sizes, each creating a different experience for anything unfortunate enough to fall in, but all sharing the fundamental property of having an event horizon, a singularity, and the ability to trap anything that crosses the boundary. We have explored what you would experience falling into a black hole, but what would someone else see if they watched you fall from a safe distance? And the answer is strange, revealing another aspect of black holes that challenges our intuitions about space and time. If a friend stayed behind while you fell toward a black hole, watching through a telescope, they would see something very different from what you experience, and this difference comes from time dilation, the slowing of time in strong gravitational fields as predicted by general relativity. As you approach the event horizon, your friend would see you moving slower and slower, your movements becoming sluggish, as if you were moving through thick syrup, and this slowing would become more and more pronounced the closer you got to the horizon. Light from you would also be redshifted, shifted toward longer wavelengths, becoming redder, and this redshift would increase as you approached the horizon, and combined with the slowing of your motion, you would appear to dim, becoming fainter and redder as time dilation increased. From your friend's perspective, you would never actually cross the event horizon. You would appear to slow down asymptotically, getting closer and closer, but never quite reaching it. And eventually you would fade from view, your light so redshifted and dim that it becomes undetectable. But technically, you would appear frozen at the horizon forever. This is not an optical illusion. It is a real effect of how space-time is curved near the black hole. And from your friend's perspective, an infinite amount of time would need to pass before you crossed the horizon, meaning they would never see you cross. You would be frozen there forever from their viewpoint. But from your perspective, you cross the event horizon in finite time, perhaps just a few seconds or minutes depending on your trajectory, and you experience nothing special at the horizon, continuing smoothly inside. And both perspectives are correct. They are just describing the same event from different frames of reference in curved space-time. This is one of the strangest features of black holes, the complete disagreement between perspectives, and it shows how profoundly gravity affects not just space but time, creating situations where observers disagree about basic facts like whether an event has happened yet. Your friend would see you stretched as you approached, the tidal forces elongating your body, and they would see this stretching increase, but because of time dilation, they would see it happening in slow motion, stretched out over what seems like forever from their perspective, asymptotically approaching the horizon. Eventually you would fade completely from view, your light too redshifted to detect, and your friend would be left looking at the black hole, which would appear unchanged, just a dark circle, with no visible sign that you had fallen in except perhaps a tiny increase in its mass, far too small to measure. The information about you would seem to be lost. From your friend's perspective, you disappeared, frozen at the horizon and then faded away. And this raises deep questions about what happened to the information that described you, your structure, your memories, everything that made you unique. This is part of the black hole information paradox, the question of whether information is destroyed when something falls into a black hole. And this paradox connects quantum mechanics to gravity and remains one of the deepest unsolved problems in theoretical physics. So the experience of falling in and the experience of watching differ completely. You experience a finite time journey from approach to horizon to singularity, while your friend sees you slow down, freeze, and fade, never witnessing the crossing, and both views are valid descriptions of the same events in different reference frames. This teaches us that space and time are relative, not absolute, and that gravity affects time as profoundly as it affects space, and black holes, by creating extreme gravity, demonstrate these relativistic effects in ways that nothing else can. Understanding this difference in perspectives is crucial for understanding black holes, because the interior is forever hidden from outside observers, not just because light cannot escape, but because, from outside, the crossing of the horizon occurs at infinite time, meaning it never happens from the external perspective. Yet we know matter does fall in, black holes do grow, and somehow this paradox must be resolved, and physicists continue working on this, exploring ideas from quantum mechanics, from information theory, and from various approaches to quantum gravity. Rest now with these two perspectives, yours as you fall, experiencing the journey in finite time, and your friends as they watch, seeing you frozen forever at the horizon, and appreciate that both are true, both are valid, and both teach us something profound about the nature of space, time, and gravity. Let the strangeness settle, not as something confusing, but as something beautiful, a demonstration of how the universe works at its most extreme, where our everyday intuitions fail, but where mathematics and physics provide clear descriptions, even if those descriptions seem paradoxical from our limited human perspective. We return now to safety, to Earth, to the present moment, having completed our imaginary journey through spaghettification, from approach to black hole through event horizon to singularity, and having learned about tidal forces, time dilation, and the extremes of gravitational physics. This was a thought experiment, a safe exploration, and its value lies not in the violence of the imagery, but in the understanding it provides, the insights into how gravity works when it becomes truly extreme, when space-time curves so dramatically that it transforms everything that enters into something unrecognizable. Spaghettification is a real phenomenon, predicted by general relativity, and while no human will ever experience it, understanding it teaches us about gravity, about structure, about the limits of matter's ability to resist deformation, and about the mathematical beauty of Einstein's equations describing these extreme situations. Black holes are laboratories where physics reaches its limits, where our theories are tested in conditions we can never recreate on Earth, and where we learn about the fundamental nature of space, time, and matter by contemplating these extreme objects. We study spaghettification not because we fear it, but because understanding it helps us understand everything else. The nature of tidal forces on Earth and Moon, the structure of matter, the relationship between gravity and space-time, and the deep questions about information, entropy, and the ultimate fate of matter in the universe. The journey we took tonight was gentle despite its subject, moving slowly through each stage, understanding the physics at each step, and seeing how gradual processes can become extreme when gravity intensifies, and this gradual approach is part of what makes black holes so interesting. They are not instant destroyers, but patient transformers. Black holes remind us that the universe operates on scales far beyond human experience. From the gentleness of gravity on Earth to the violence near a singularity. And exploring these extremes expands our understanding and helps us see our place in the cosmos with greater clarity and humility. There is beauty in understanding what would happen, even if it never will happen to us, because this understanding connects us to the universe, shows us how nature works at its limits, and demonstrates that the cosmos follows laws, predictable mathematical laws, even when those laws produce results that seem impossible or extreme. Spaghettification shows us that structure is fragile, that the organization that makes up stars, planets, and living things can be undone by force, that matter is malleable, and that gravity, given enough strength, can reshape everything. And this knowledge is sobering but also empowering, showing us the power of nature. But it also shows us that we understand this power, that we can predict what happens, calculate the forces, describe the transformation mathematically, and this understanding is humanity's great achievement, our ability to comprehend the universe through observation, mathematics, and careful reasoning. Black holes were once purely theoretical, predicted by equations before being observed, and now we have detected them, imaged their shadows, measured their masses and spins, and we continue to study them, learning more with each observation, and spaghettification is part of this ongoing exploration, a prediction we cannot test directly but can understand through physics. The thought experiment of falling into a black hole is valuable precisely because it is impossible. It pushes our imagination, challenges our intuitions, and forces us to think carefully about space-time, about the difference between perspectives, and about what happens when gravity becomes the dominant force, overriding everything else, including the structures that define us. So, we end this journey with gratitude for the opportunity to explore safely, to learn about extreme physics, and to see the universe through the lens of general relativity, appreciating both the beauty of the mathematics and the power of gravity in its most extreme form. Rest now, knowing you are safe, that Earth's gravity is gentle, that black holes are far away, and that this was all imagination, all peaceful exploration, and the knowledge you gained is real and valuable, even though the experience itself was theoretical. Let the images fade, let your mind settle, and appreciate that we live in a universe that is knowable, that follows laws, and that rewards careful study with understanding, and black holes, though extreme, are part of this knowable universe, waiting to teach us more as we continue to observe and explore. Thank you for traveling with me tonight through this strange journey, from the approach to a black hole through spaghettification to the singularity, and I hope you found something calming, something fascinating, or simply a moment of peace in contemplating these extreme ideas. Black holes will always be there, far away but real, teaching us about gravity, challenging our theories, and reminding us that the universe is more extreme and more wonderful than our everyday experience suggests. Until next time, rest well, let the stars watch over you, and remember that understanding extreme things helps us appreciate normal things, that contemplating black holes helps us appreciate Earth, and that exploring the impossible in imagination is part of what makes us human, curious, and connected to the cosmos. Good night, and may your dreams be peaceful, filled with wonder rather than fear, with understanding rather than confusion, and with the knowledge that even the most extreme phenomena in the universe follow laws we can understand, and that this understanding brings not terror but awe, not anxiety but peace. As you drift towards sleep, let the concept of spaghettification fade, knowing it was just a thought experiment, a way to understand physics and not something to worry about or fear, because black holes are far away and we are safe here on Earth. The stretching we described was extreme but also gradual, beginning gently, building slowly, and only becoming destructive very close to the singularity. And this gradualness is part of what makes physics beautiful, showing us that even extreme phenomena follow predictable patterns, building step by step rather than happening instantly and chaotically. Tidal forces exist everywhere, even here on Earth. They create the ocean tides, they affect satellites in orbit, and they are part of how gravity works on extended objects. And understanding them near black holes helps us understand them everywhere, seeing the same physics at work across vastly different scales. So the journey was educational, showing us how physics scales from gentle to extreme, and how the same equations that describe Earth's gravity also describe black holes. And this unity of physics, this consistency across scales, is one of the most beautiful features of our universe. Black holes are not enemies or threats. They are simply objects in the universe, extreme objects that follow the same physical laws as everything else. And studying them enriches our understanding without creating any danger, because understanding and experiencing are completely different. And we can understand black holes without ever needing to approach one. The scientists who study black holes do so with wonder and curiosity, not with fear, and they see these objects as opportunities to test theories, to learn about space-time, and to push the boundaries of what we know. And this scientific approach, focusing on understanding rather than emotion, is part of what makes science such a powerful tool for exploring reality. Tonight, you joined that exploration, using your imagination to follow a journey that will never happen, but that teaches us real physics, real mathematics, and real insights into how the universe works at its most extreme. And this kind of exploration is valuable, enriching, and ultimately calming because it shows us that the universe makes sense. So rest peacefully, knowing that tonight's journey has ended, that you are safe, that black holes are fascinating rather than frightening, and that understanding them is part of understanding the cosmos, part of being human, and part of the endless quest for knowledge that defines our species and connects us to the stars. Sleep well tonight, and let the concepts settle into your subconscious, where they can blend with dreams, with other knowledge, and with your growing understanding of the universe. And know that each thing you learn, even about extreme phenomena like spaghettification, adds to your picture of reality and makes you more connected to the cosmos around you. The universe is vast and contains wonders beyond imagination. From the gentle pull of Earth's gravity to the extreme tidal forces near black holes, from the peaceful rotation of planets to the violent death of stars, and all of it follows laws, patterns, mathematics that we can discover and understand if we are patient and curious. Tonight, we explored one small corner of this vast landscape, the journey into a black hole, and we saw how gravity transforms everything when it becomes strong enough. And this exploration has given us knowledge, perspective, and hopefully a sense of peace in knowing that even the most extreme things can be understood. So drift towards sleep now, let your body relax completely, and let your mind wander through space, knowing that black holes exist but are far away, that spaghettification is real but not a threat, and that understanding these things makes the universe more knowable, more beautiful, and ultimately more peaceful to contemplate. Good night, and may your dreams carry you gently through the cosmos, where stars shine, galaxies turn, black holes bend space-time, and everything follows the elegant laws of physics that we are slowly learning to understand. Thank you for exploring with me tonight, for following this thought experiment to its conclusion, and for appreciating the beauty of extreme physics presented gently, calmly, and with wonder rather than fear. Until next time, rest deeply, sleep peacefully, and know that the universe is knowable, that science reveals its secrets through patient study, and that even the strangest phenomena, when understood, become part of the beautiful tapestry of cosmic knowledge that humanity is weaving across the centuries. Sweet dreams, and may the stars watch over you, bringing not terror, but comfort, not confusion, but clarity, and reminding you that we are all part of this vast cosmos made of stardust, bound by gravity, and blessed with the ability to understand the universe that gave us birth.